Let us talk about recursion. A classical function that we can write in a recursive fashion is a factorial. The factorial of n is equal to the product from k that goes from 1 to n of k. So this suggests an iterative definition of factorial. We see it here. We set that the product equals to 1. The product of zero numbers by definition is 1. And then we iterate for k that goes from 1 to n. This range stops at n. And we multiply the product times k and we return the product. So this is a perfectly good definition, an iterative one. But we can also go for a recursive definition. So essentially, we can write that the factorial of n is equal to n times the factorial of n minus 1, if n is greater than 1, or greater than 0 actually, and is equal to 1 if n equals 0. Okay, so we can use this definition, which leads to this code, okay, which is quite compact, and this also perfectly works. Okay, so it's a matter of taste which one of the two you want to use. And here the point is not so much which one of these two is more efficient, but is rather the principle we have used in defining our recursive function. So we see that we reduce the factorial of n to the one of n minus 1. So here we can see at work in a very simple example the two basic ideas we use in recursion all over the time. The first idea is we reduce a problem to a simpler one. And how it is simple, in this case, is you go from n to n minus 1. You could go from a problem on a big object to a problem on a big object in which you have cut away a piece that is not there anymore, right? So the object became smaller somehow. You can go from a number to a number that is smaller, or there are many ways in which you can simplify the problem. But the general reason why you may want to use recursion is that a problem, solving it directly may be hard, but if you reduce it to a smaller problem, then you may be able to solve it. So essentially, instead of worrying about the entirety of the problem at once, you just worry about how to solve a smaller problem and how to build your solution out of the smaller one. We see here exactly this procedure, right? So this is a smaller solution, and this is how we go from the smaller solution to the solution to our problem. Okay, so this is the first idea, which consists in why do we use recursion at all. And the second idea is the following. Termination. So whenever you have a recursive function, just as whenever you have a loop, but recursive functions are typically more troublesome, whenever you have a recursive function, you have to worry, why does it terminate? If the function calls itself, how can I know that this sequence of calls at some point will end rather than lasting forever? In fact, if you write code, it's quite common to make mistakes while you are writing it and initially write it wrong in such a way that the sequence of chains never stops. So how do you ensure that it stops? Basically, imagine that you call your function for a value, and then these calls in turn the function for another value and then for another value. You have to show two things. You have to show that this sequence of values is descending. Okay, so every value has to be smaller than the previous one according to some ordering. For example, if you're working with numbers, the number may be smaller. If you're working on strings, the string can be shorter, something like that. And the other thing that you need to show is that in the end, this thing does not go on forever. So it is a finite, always a finite descending chain. So in particular, it should not be possible to go down ad infinitum, okay? And that is what you use to show termination. In the case of factorial, it's easy. The factorial function accepts non-negative integers, and in the way we have defined it, we reduce ourselves to a smaller integer as long as we are above 0, but at 0 we stop. And so you can go down only so many steps before you reach 0. Let us look at another case when we can use recursion. This is Fibonacci numbers. So they are defined as follows. Fibonacci of 0 is equal to 0. Fibonacci of 1 is equal to 1. Fibonacci of n, of course for n greater than 1, is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So this immediately suggests a recursive implementation in which we have these two base cases, and this recursive case is n is greater than 1. We can then proceed to write this quite elegant code, which just summarizes our definition. Okay, notice how I use this inline if-then-else to write more pleasant code. This works perfectly. Well, almost perfectly. The problem is this: every call to Fibonacci of n causes two recursive calls. Before, the factorial caused only one recursive call. This causes two. And so, because you stop only when you reach 0 or 1, this in general will cause, if you increase n by 1, you roughly get twice as many calls, because you get all the calls for n minus 1 and all the calls for n minus 2, right? So this is roughly exponential. I mean, it is exponential. It is roughly proportional to 2 to the n. Not quite, but close. Okay, so in fact we can use a global variable number of calls to keep track of the number of calls, and we increment it for each call. So look at it. When we ask Fibonacci of 10, these will require 177 calls. Fibonacci of 11, these will require 287 calls. So this is actually not very nice. So you have to be careful sometimes with a recursion at how many recursive calls you call. Is there a better way to do it? Is there another approach if these calls are large? You will learn in discrete math courses how to precisely measure the number of calls. What I pay attention to here is just an order of magnitude, right? So to obtain an efficient version of the as algorithm, there are two ways. One is to give up recursion and move to iteration, which is perfectly fine and probably the best for this problem. And another one is a technique called memoization, which consists in remembering the output of the return values of calls to the recursive function that you have already done, so that you don't have to call the same function multiple times for the same value. In the examples we have seen so far, recursion is used as a way to perhaps write an elegant solution, but a more efficient solution could have been written by simple iteration. So let me show you now a case in which recursion really helps. I will be describing the Euclidean algorithm, which is generally considered the oldest known algorithm. This dates from the times of Euclid in Alexandria of Egypt, 2000 years ago and counting. So the idea is this: we want to compute the maximum common divisor between two numbers, m and n. This is the Euclidean algorithm. Okay, and the idea is as follows. Look at m and n, and then look also at m modulo n and n. So this is, the remainder, I call it R, of the division of m by n. Now, the idea is that these two numbers and these two numbers here on the left and right, they have the same divisors. Okay, the m and n and m modulo n and n have the same set of divisors. So if you want to find the maximum common divisor between m and n, you might as well reduce yourself to the simpler problem of looking for the maximum common divisor between m modulo n and n. This is an example of a reduction to a simpler problem. So you can convince yourself that these two pairs of numbers have the same divisors. I will show it in one particular direction. Imagine that Q is a divisor of both m and n. if you have one such common divisor k, you can write m is equal to ak, because k divides m, and also n is equal to bk for some other b, okay? So on the other hand, m can be written as c times n, where c would be the quotient of this division, plus the remainder. And so we can substitute and we can write ak is equal to c times n, which is bk, plus the remainder. And so gathering, we can write that the remainder is equal to a minus cbk. And so k will divide both n, as before obviously, but also it will divide the remainder. So if k is a divisor of both m and n, it is also a divisor of both n and the remainder. Okay, and you can show also the reverse implication. So essentially going from n and n to m modulo n and n does not change the set of common divisors. Okay, and so the idea is this: you keep doing this substitution as long as you can. When is it that you no longer can do this reduction? Well, when you cannot do anymore this division. That is, you have to stop when n equals 0, because you cannot take the modulo 0, right? So, but that's an easy case to deal with, because if you have at some point m and 0, then you know the answer, because what is the maximum common divisor between a number and 0? Well, it's just the number itself, right? And so we can use this idea to write the Euclidean algorithm as follows. So here, the maximum common divisor between m and n, I reorder them in such a way that m is bigger than n, and then I say return m if n equals 0, else return the maximum common divisor between m modulo n and n. This is exactly what we gave in our definition, okay? And so this works. How can we prove termination? There are various ways. Actually, I think the simplest would be just to consider the sum of m plus n and to show that that decreases. Here I give another argument. You can use various arguments for termination, but there is more than one proof and it works. Let us now consider another case in which recursion helps, and that is permutations. So, assume that you have a set of elements, for example, 1, 2, 3, and you want to compute all the permutations of these elements. This will be essentially a bigger set containing the tuple 1, 2, 3, then the tuple 1, 3, 2, then 2, 1, 3, then 2, 3, 1, and then, two more tuples that begin with a 3. Okay, so how can we do it? So if we do it by hand, one idea is the following. We can write 1, 2, 3, and we can say, well, I need to first pick out what the first element is of the permutation. So I can pick out as first element these, and then I'm gonna pick out these, and then I'm gonna pick out these, okay? Once I pick out the first element, I need to pick out the second element, excluding what I have already picked out, and so on and so forth. So I can imagine that I can write a loop that works something like this. I can say S0 is equal to S, just for uniformity of notation, and then I can say that the result is the empty set so far, and then I can say for x0 in S0, so I pick out the first element, and then I say the remaining set is equal to S0 minus x0, okay, and then I say for x1 in S1, no, so this would pick out the second element, and then I don't know exactly how I would continue, and then I would say result dot update to add an element to the set, and I would write here the tuple x0, x1, and so on and so forth. Now, this doesn't quite work, and the problem is that you need as many for loops as there are elements in S. And so a purely iterative solution done in this way cannot work, because you don't know how S is big, you don't know how many loops you need a variable number of loops. So that's not the idea we are gonna use. We are gonna use instead recursion to reduce this problem to a simpler one. So the idea is this: if we have a set S of elements, for example 1, 2, 3, 4, to produce a permutation of S, we do as follows. We take in turn for X all the elements of S, one after the other, right? And then we concatenate with X P for P that is a permutation of S minus X. That is, a permutation of S is obtained by first picking an element X of S, picking all the elements in turn, and then concatenating with X a permutation of the remaining elements. So if we have this idea, if we move it to code, we obtain the following. So in formulas, the set of permutations of S is equal to the union for the elements of S, the union of the permutations of the remaining elements of X concatenated with a permutation of the remaining elements. And in code, this is easy to write. The permutations of S, so we take care of the base case, of course. So if S is empty, we just return the empty permutation. Otherwise, we initialize the set of all permutations, our result set, to the empty set, and then we iterate over the elements of our set. And for each one of them, we add to the permutations the concatenation of X and P, where P is a permutation of the remaining elements. This funny notation X comma is just to generate a tuple containing only one element. So this works. For example, we can say permutations of 1, 2, 3, permutations of 1, 2, 3, 4 if we wish. Okay, and we get this bigger list of permutations. You see, we alternatively pick the first element, and then concatenated with the first element are the permutations of the remaining elements. That's the idea we use. So I want to give you a final advice about how to try to reason about code that uses recursion. So the way that I see many people doing is this. There is a function, and to understand what the function does, you say, oh, okay, the function calls itself one more time, and this function calls itself one more time, and this function calls itself one more time, okay, and so on and so forth, till at some point the results all pop out again. And so you try to essentially go through your mind, through this recursion, running the code in your mind. And what I want to tell you is that your mind is not really made for working into this kind of rabbit holes. Okay, your mind is not done for keeping more than a few things in mind at the same time. And so this is a particularly difficult and in the end useless way of thinking about recursion. The way you should try to understand any piece of recursive code is the following. You should consider two cases only. Okay, in one case, you say, okay, I have my function f that calls itself once more. What it does in this particular invocation, so how the code works, you don't consider it. You consider this as a sort of black hole, and the only thing you consider is what it gives back to you. Okay? But you do not run the recursion in your mind. You simply trust that f called on a smaller argument will work fine, and try to understand why also in your case it will work fine. This is sort of the inductive case of the argument, and it's one of the two cases that you have to consider. And the other case is simply that f sometimes will not call itself, okay, but it will simply compute what it needs from scratch. So this is a base case. For example, when one of the integers is 0 in the maximum common divisor, or else when the set is empty for the permutations. Okay, you need to understand that these two things only. You need to understand the base case that is correct and does what it needs, and you need to understand the induction case. So this is the induction case, and you need to understand the induction case, assuming that your function works fine for smaller arguments, show that it also works fine for the larger one you are considering. Okay? And this is all you have to do. Do not try to run the code in your mind. You will in truth not gain much more understanding and will simply confuse yourself, because it will be quite time consuming and mind-boggling really to try to run it mentally. And there is absolutely no need for this. This should be the simple picture and the simple goal of your understanding.